Hello guys, good evening, and in this video I will be solving chapter 1 of the Faires and Simmang thermodynamic book. And here in this video I have prepared 5 practice problems, and I will be solving each problem and also explain the steps and how to solve the problems. So let's start. For let me just put in the number. For problem number 1, a 30-meter vertical column of fluid density 1878 kilograms per meter cube is located where gravity is at 9.65 meters per second squared. Now, find the pressure at the base of the column. So first things first, before you solve any type of problem, the best thing that you would do is list down the given values. So the height is given as 30 meters. And then the fluid density is also given. Fluid density is equivalent to 1878 kilograms per meter cube. And then lastly, gravity is at 9.65 meters per second squared. Okay, and remember, the general equation and or formula for pressure, hydrostatic pressure, is given as pressure is equivalent to density, gravity, and height. So since density is given, gravity is given, and height is given, so all you have to do in solving this problem is substitute the given values. So density is given as 1878 kilograms per meter cube, and then gravity is at 9.65 meters per second squared, and then height is at 30 meters. So the unit for pressure is either Newton per meter squared, kilonewton per meter squared, or in English system that will be pound force per inch squared or pound force per feet squared. So in order to create a unit of Newton, we need a unit of kilogram, a unit of distance, and a unit of time. So kilogram meter per second squared, that is equivalent to Newton, and then meters divided by meter cube, that would give us Newton per meter squared. So we cancel this one, we cancel 3, and we replace it by 2. So kilogram meter per second squared, that would be Newton, and then all over meter squared. So multiplying the values, we will have 1878 times 9.65 times 30. It will give us a value of 543,681. So 543,681, and then the resulting unit would be Newton per meter squared. So this Newton per meter squared, this will be equivalent to a unit of Pascal. And then if you want, we can convert this one into kilopascal. So pressure would then be dividing the given value of, the resulting value of 543,681 by 1,000. This will give us 543.681 kilopascals. Alright, so that would be the answer for practice problem number 1. And then just fold this one. Let's jump on to practice problem number 2. If a pump discharges 284 liters per minute of water whose density is 985 kilograms per meter cube, find the mass flow rate in kilograms per minute and the total time required to fill a vertical cylindrical tank with a diameter of 3.05 meters and a height of 3.05 meters. So again, we will be listing the given values. If the pump discharges at 284 liters per minute of water, so that would be volume flow rate. So I'll just use this symbol in order to differentiate volume flow rate from volume. So volume flow rate would then be 284 liters per minute And then another given is the density of water. The density of water is at 985 kilograms per meter cube. And then we would be solving first for the mass flow rate. Let's put letter A. The value of mass flow rate is unknown. So we know, in solving this, we know that density is defined as mass all over volume. So if the given volume is volume flow rate, therefore we will be able to, if we transform the formula, if we will transform it into mass is equivalent to density times volume flow rate, then the given mass, the mass that we would get, the value of the mass we would get, and its unit would be in mass flow rate form. So in solving for the mass flow rate, since we are given with the volume flow rate, we would just use this formula and then substitute the values. So density is 985 kilograms per meter cube, and then the volume flow rate is given as 284 liters per minute. Alright, since the two units for volume are not uniform, meter cube and liters, we would then convert liters into meter cube, and the conversion is 1 meter cube is equivalent to 1000 liters. So by cancelling the units, meter cube would be cancelled, liters would then be cancelled, and then the remaining unit would then be kilograms per minute. So simplifying, 985 times 284 divided by 1000, the answer would be 279.74. So mass flow rate is equivalent to 279.74 kilograms per minute. Okay, so let's move on to letter B. The question for letter B is the total time required to fill a vertical tank with diameter of 3.05 meters and 3.05 meter with regards to its height. So diameter is equivalent to 3.05 meters, and then height is equivalent to 3.05 meters. Since it is a since it is a cylindrical tank, the formula for volume of a cylinder, is given as pi radius squared times the height. So substituting the given values, pi times, since the given value is in diameter, so we will just divide it by 2. So 3.05 meters divided by 2, and then raising it to the power of 2 times the height of 3.05 meters. So the resulting volume is, so shift pi times 3.05 all over 2 to the power of 2 times 3.05. So the volume would then be 22.2838. So 22.2838 meter cube. And then the question is, how would we'd be able to determine the total amount time required to fill the vertical tank? So by dimensional analysis and analysis of unit, we know that volume flow rate, so let's draw the tank. So let's say this is the tank, just like that. Let's say you have a water hose, this one, and then it fills in the tank at a rate of 284 liters per minute, and then the overall volume of this tank is given as 22.2838 meter cube. So how will we be able to come up with the unit of time? So by using dimensional analysis and analyzing the units, time would then be given as volume divided by the volume flow rate. So by substituting the values, we would 22.2838 meter cube divided by 284 liters per minute. Converting liters to meter cube in order for us to have a uniform unit. So liters to meter cube. So 1 meter cube is equivalent to 1000 liters. And cancelling the units, meter cube cancel, liters cancel. So since minute, the unit of time, is at the denominator of our denominator, so it will then flip to the top, or the reciprocal of this one, since if we use the law of fraction, dividing fractions, a over b divided by c over d is equivalent to a over b times d over c. So a here is 22.2838, b here is 284 liters, and 22.2838 meter cube would be a, b would then be 1, 284 liter would then be RC, and D would be 1. So time is equivalent to 22.2838, since the reciprocal of this, minute, will go on top, and then all over 284 divided by 1000. Solving for time, simplifying, 22.2838 divided by 284 divided by 1000. So the answer would then be 78.464 78.464 minutes. So the time required to fill the vertical cylindrical tank with the volume of 22.2838 meter cube, given that the volumetric flow rate is 284 liters per minute, would require a time of 78.46 minutes. Okay, that's for question number 2. Now let's proceed to problem number 3. A weatherman carried an aneroid barometer from the ground floor to his office atop the Sears Tower in Chicago. On the ground level, the barometer read 30.15 inches of mercury absolute. At the top side, it read 28.607 inches of mercury absolute. Assume that the average atmospheric pressure air density was 0.076 pound per cubic feet, and estimate the height of the building. So, in order for us to solve this problem, we need to draw it first, so that we'll be able to visualize the problem itself. So let me just put here question number 3, and then let's draw a simple tower. Our main objective is to solve for the height. So the tower looks like this, and then let me just put the ground floor. Based on the situation at the ground level, so I'll put this one as pressure 1. The barometer reads 30.15 inches of mercury. Then at the top of the tower, at this point, the barometer reads 28.607 inches of mercury. Both is in absolute form. And then, in order for us to to estimate the height of the building, we must need to have a base of our pressures. I'll call this one pressure 2. Since the pressure when you go outside, the pressure, atmospheric pressure, they are all based from the distance from the atmosphere. The closer you are to the atmosphere, so the value of our atmospheric pressure decreases. So when you are at the atmosphere, the pressure ATM, or pressure of the atmospheric, of the atmosphere is 0. So that means the farther you are from the atmosphere, the greater the pressure is. Just like for example, pressure 1 is greater than pressure 2. Since pressure 2 is closer, let's say, let me just put a line here. So let's say this line here is the atmosphere. Since pressure 2 is closer to the atmosphere, that's why it is way lower compared to the pressure at the ground level, since the distance from the atmosphere towards the ground level is a factor, and also the gravitational pull. The closer you are towards the Earth's core, the greater the gravitational pull is, and that's why the greater the pressure is. So, in order to estimate the height of the building, we must need to apply this kind of analysis. So first, let me put my variables. So the distance from the atmosphere towards the ground floor would then be height number 1, and then the distance from the atmosphere towards the top of the building, I'll put this as height 2, and then I'll put this the height of the building would then be h. So if you apply algebra, we will be able to summarize that height of the building is equivalent to height of h1 minus h2. So this will then be our equation number 1. And then the next thing that we would do, we know that pressure is defined as density, gravity, height. And since the heights are the ones that are in our equation 1, so what we're going to do is we need to transform this formula for pressure and solve for height. So height is equal to pressure all over density times gravity. So substituting this transform formula to our equation 1, we'll be able to get height of the building is equivalent to pressure 1 all over density gravity minus pressure 2 all over density gravity. Just like that. And then let's simplify this equation. So height of the building is equivalent to 1 over density gravity times pressure 1 minus pressure 2. So the formula now is much more simpler compared to this one. So what we're going to do now is we just need to substitute our values. So height of the building is equivalent to 1 all over density. Density is given as 0.076 pound per cubic feet. So substituting that one to our equation, so 0.076 pound per cubic feet. And then the gravity, the value of gravity in English system, so that we'll be able to have a uniformity of units. The value of gravity in English system, since there is no specified value of gravity, so we are going to assume that it is in standard condition. So at standard condition, gravity is 32.174 feet per second squared. Like that. And then pressure 1 is 30.15, and then pressure 2 minus 28.607, and then the unit would be inches of mercury, and that would be absolute. Just like that. Simplifying the equation. So in order for us to have a unit of force, we need a unit of mass, a unit of distance, and a unit of time. So that would be in English system, in metric system, we need kilogram meter per second squared, and in English system we need slug feet per second squared. So our given here, the unit of mass is in pound mass, so we need to convert pound mass into slug, so that if we combine slug feet per second squared, we'll be able to come up with a unit of force, which is pound force. So 1 here at top, 0.076 pound mass per cubic feet times 32.174 feet per second squared, and then converting pound mass to slug. So 1 slug is equivalent to 32.174 pound mass. And then simplifying 30.15 minus 28.6057, 30.15 minus 28.607, 1.543. So 1.543 inches of mercury absolute. So simplifying this side of the equation, so pound mass cancel, and then 32.174 cancel. So we'll have a unit of slug feet per second squared that would be in pound force all over cubic feet. So the equation becomes 1 all over 0.076 pound force. Since we will be combining slug feet per second squared, that will become pound force all over cubic feet times 1.543 inches of mercury, and that's in absolute form. So the same thing in problem number 2. Since the denominator of our denominator is cubic feet, so this would then flip to the top. A over b divided by c over d is equal to a over b times d over c. So cubic feet goes to our numerator. So cubic feet here, and then 0.076 pound force at the bottom. And then in order for us to cancel out pound force, because we only want a unit of height, it will either be in inches or in feet, we need to cancel out pound force. So we need to convert our inches of mercury into PSI, because PSI stands for pound force per inch squared. So the conversion would then be is 14.7 PSI all over 29.92 inches of mercury. So cancel inches of mercury. So we will have a unit of PSI, cubic feet, and pound force. So we need to simplify PSI into pound force per inch squared. So rewriting our equation and simplifying, cubic feet here, and then 0.076 pound force at the bottom, multiplied by 1.543 all over 29.92 times 14.7 and pound force per inches squared. So we can now cancel pound force, and our remaining units are cubic feet and inches squared. So since they are not uniform yet, we need to convert either one of them. So I'll be converting inches squared into feet squared. So inches squared, 144 inches squared, that would be 1 foot squared or feet squared. Canceling inches squared and feet squared, cubic feet divided by feet squared. So the remaining unit would now be in feet, or in feet. So height of the building is equivalent to simplifying and multiplying everything that we have arrived with. So 1.543 times 14.7 times 144 divided by 0.076 times 29.92 is equivalent to 1436.384 feet. So that means the height of the building is approximately 1436.384 feet. So that's for question on problem number 3.